So this is J.J. Thomson, one of the great figures in physics, who spent his career at the Cavendish Laboratory at Cambridge University, and he's most famous as the discoverer of the first elementary particle, the electron, in 1897. So it's actually kind of mind-boggling to realize that just over 100 years ago, not just the structure, the constituents of the atoms, but even the existence of atoms was still being actively discussed. I mean, in the landscape of history, that's pretty much yesterday. So he discovered the electron in 1897, and then a few years later, he proposed what's known as the plum pudding model of the atom. Now, as I discovered reading, and hopefully people from the UK can confirm it, it seems plum puddings actually don't have plums, they have raisins. These days, it probably would be called a blueberry muffin model of the atom. The idea is that the atom is a ball, a mass of positive charge, and electrons are embedded in it. Now, just a few years later, Thomson's student Rutherford discovered that this is not how the atom is constructed. Atoms actually have nuclei in the middle, and electrons spin in orbits around it. And so these days, when the plum pudding model is mentioned in textbooks, it's more like a historical curiosity and, you know, with a little bit of a dismissive statement, like you can see here, pulled from one of the textbooks, and kind of like, yeah, JJ, you were a brilliant scientist, but you really whiffled on this one. So now with this, I'm going to switch gears for just a moment and tell you about the research area that I work in. So, you know, we're all taught that matter is made of atoms. You put a few atoms together, you make molecules. You put a bazillion molecules together, you make bulk liquids or solids. To a person like me, there is a missing link here. The missing link will appear in just a moment. This is what we call atomic clusters or nanoclusters. Basically, the idea is you start with an atom, you add another atom, you add another atom, and we want to understand how these small particles that have a few tens, hundreds of atoms or molecules gradually develop into solids or liquids as they grow one atom at a time. So you can make these things out of almost any atom and molecule these days. There are instruments to do this, but I want to talk about metal, clusters of metal atoms. How do we make them? So let me back it up for a second. One way to make them is to generate a vapor of metal atoms by heating them up, for example, and then expanding them through a pinhole into vacuum. The jet cools down and the atoms condense into small particles. It's the same physical effect as people use for making artificial snow, for example. So here, if you wish, we make metal snow. And then once we make them, we can start by looking at how many clusters of different sizes are actually in the beam, how many are created. And there is a fascinating discovery that was made at Berkeley and published in 1994 by my future PhD advisor, Walter Knight. This was before I joined the group, so I can remain modest and say this was a really fascinating discovery. They looked at clusters of sodium atoms to begin with. Sodium is a simple metal, kind of like the fruit fly of solid state physics. And as you can see in this plot, they discovered that certain cluster sizes were way more stable than their neighbors. These, by analogy with nuclear physics, are known in the business as magic numbers. And when you look at this, one of the things that comes to mind, or should come to mind, is that it's very similar to how the periodic table contains really unreactive atoms. And to make a long story short, what was realized is that they actually have a lot of similarity. Atoms have electrons spinning around the positive nucleus in electron orbits. If you mentally replace the positive charges in the cluster by a sort of uniform positive blob, the electrons spin in orbits inside that cluster, and they also form electronic shells. And you have a very similar pattern of electron orbits. So in fact, what you encounter and what we see here is electronic shell structure of metal clusters. Sometimes they're called superatoms. And some people say that this kind of extends the periodic table into the third dimension, because you can now choose the element and you can choose how many atoms of the element you put together, how many electrons form the orbits. And the thing that's interesting is that in a way, what I'm trying to say here, it's a reincarnation of the plum pudding model. It's a blob of positive charge with electrons inside it, which probably it's not a general theorem, but it kind of suggests that some really good ideas in physics really don't die, but they just kind of reincarnate in a different form. So that's the main message. One other thing that one finds is that artists often discover things before scientists do. So I found this cover of a comic page of a comic issue from 1959. As you can see, they already talk about superatoms. So that already existed. And then in the last few seconds, I also want to say that these electrons in the cluster can also oscillate back and forth. So to people in the business, this is known as plasmonics. It's the same effect that you find as an ancient recipe for stained glass. In stained glass, you have nanoscale particles that are embedded in the glass. And the most famous example of that, probably, it's the Lycurgus cup, which is in the British Museum. I actually saw it in the Getty Villa near Los Angeles when they had an exhibit of British glass. It was probably the only person there admiring not just the carving, but the science. As you can see, it appears different colors in reflected light and transmitted light, and I can certify personally that is the case. And it turns out the reason for that is that the glass contains nanometer scale silver and gold particles embedded in there. And the moral here is that when we talk about our doing nanotechnology, we should be somewhat modest here because, as you can see, the Romans were already doing nanotechnology in the 4th century. Thank you for your attention.